Good afternoon, everyone. Welcome back. I hope that you had a great weekend and that everybody's doing fine today. We're looking today at lesson 31.05, which deals with something called the second derivative test and concavity. And this lesson can be found on page 2 of your new lesson handout, which is the rest of the story, part 2. I'd like to review with you briefly here the meaning of a derivative being positive and the meaning of a derivative being negative. And this is something you already know, but I don't know that I've stressed something to you that is really important for today. This says, recall that when the derivative of a function is positive, then the function itself is increasing. All that's saying is if the derivative is positive, the slope is positive. But I want to draw your attention to something that's very important for what we're going to be dealing with today. And it's that when the derivative of a function is positive, it's the function that's increasing. And I want to try to give this to you in a very general sense. If I found the derivative of velocity to be positive, then that's telling me that velocity is increasing. If I found the derivative of electrical current to be positive, then electrical current would be increasing. If I found the derivative of the mouse population in an old abandoned barn is positive, then the mouse population in the old abandoned barn is increasing. So whatever it is the derivative of, that is the thing that is changing. As well, obviously, if the derivative of a function is negative, then the function itself is decreasing. So why is that useful? Well, we want to talk about the second derivative and what the second derivative being positive means, or what the second derivative being negative means. Well, the second derivative is the derivative of the first derivative. So the second derivative is telling us what is happening to the first derivative. Now keep in mind the first derivative is slope. So the second derivative is telling us what is happening to the slope of the function, because the second derivative is the derivative of the slope. What that means specifically is that if the second derivative is positive, then the slope is increasing, because the second derivative is the derivative of the slope. So if the derivative of the slope is positive, the slope is increasing. Similarly, if the second derivative happens to be negative, since the second derivative is the derivative of the slope, if the second derivative is negative, then the slope must be decreasing. And you may have to read over these two statements a few times to appreciate them. By the way, we have certain names for what these shapes are. This shape is called concave up. So a concave up shape is a shape that if you were to put this out in the rain, water would collect inside of the shape. Whereas concave down is a shape that if you put it out into the rain would pour off of it and it wouldn't collect. So if the second derivative is positive, that is the overall shape. Now, why is this an increasing slope? Well, I'm going to just illustrate this by picking some numbers here. This represents an increasing slope, or an increasing first derivative. What I'm going to do is just label a few points on here. I'm going to label this point here, and I'm going to estimate the slope there to be -3. I'm going to put a point here, and I'm going to estimate the slope here to be -1. If I put a point at the bottom where there's a minimum, we know the slope is 0 there. And I'm just going to estimate the slope here to be 2/3. I want you to notice that as you go from left to right, the number that represents the slope is getting larger. From -3 to -1 is an increase. From -1 to 0 is an increase. From 0 to 2/3 is an increase. So that's why this shape has what we call concave up. It has an increasing slope. We could do the same kind of thing with concave down. If I estimated the slope here might be 4. The slope here might be 1. The slope at the top is, of course, 0. And then over here someplace, the slope might be, doesn't really matter, -1/3. And as you go from left to right, you go from a slope of 4 to a slope of 1, that's a decrease. You go from a slope of 1 to a slope of 0, that's a decrease. You go from a slope of 0 to a slope of -1/3, that is also a decrease. And that is why when you have a decreasing slope, which means the first derivative is decreasing, which means the second derivative is negative, that is why we have this concave down shape. Now, if there is a point where the function exists, but it is not concave up at that point and it is not concave down at that point. In other words, the second derivative is not positive and the second derivative is not negative. We call that point an inflection point. And by the way, in Math 30-1, your inflection points were always on the x-axis, and that does not have to be the case in Math 31. At an inflection point, the second derivative is neither greater than 0, nor is it less than 0. So what am I saying here? I'm saying that if by definition an inflection point is where it's neither concave up nor concave down, then it's reasonable to say that the second derivative cannot be positive and it cannot be negative. The second derivative only has two options then. If it's not positive and it's not negative, then one of the possibilities is the second derivative at an inflection point could be equal to 0, and the other option is it could be undefined. These points where the second derivative is either 0 or undefined may not actually be inflection points. This is very similar to when we did first derivative analyses to determine max-min locations. What we did was we identified all the critical points of the first derivative, which were points where the first derivative either was 0 or undefined, and then we looked closer at those points to find out which of them, if any, turned out to be extreme locations, meaning turned out to be points where there was a maximum value of the function or a minimum value of the function. But we learned that not all critical points of the first derivative were max-min points. I'm telling you the same thing is going on here with the second derivative. If the second derivative is not defined, or if the second derivative is equal to 0, we call that location a critical value of x for the second derivative. And those points may or may not be inflection points. Just like with max-min points, we had to do a first derivative chart to identify which critical points were max-min points. To find out which critical points for the second derivative are actually inflection points, we must do a second derivative chart. That's a lot to take in, but we're going to do a couple of examples here. For each of the following, determine all pertinent features of the function, including concavity intervals and inflection points. So we start off with this rational function, f of x equals x over x squared plus 1. And I'm going to start compiling a list of all the things we need to know. We would need to know if there are any x-intercepts, and we would need to know if there is a y-intercept, and we would also like to know about any possible symmetry. What else do we want to know? Well, we want to know if there are any asymptotes, so let's make a note that we want to look at vertical asymptotes. we want to see if there is a horizontal asymptote. And I think that's it for now. We also want to do the first derivative chart and the second derivative chart, but we'll worry about that in a bit. So x-intercepts are where y equals 0. And if we investigate this function, this is kind of my rough work over here. I have y equals x over x squared plus 1. If y equals 0, I'm left with this equation that I need to solve. Well, the only way that x over x squared plus 1 can equal 0 is if the numerator of that is equal to 0, which means the x-intercept is equal to 0. 0 is the only 0 of this function. It's the only value of x that will make the whole function 0. So we can go back and we can put that in our list. The x-intercept is equal to 0. By the way, I don't really need to go any further to find the y-intercept, because if you were to plot a point on the x-axis at x equals 0, guess what you get for y? You also get a y-intercept of 0. We could officially show that that's the case by saying that to find a y-intercept, you let x equal 0, and if you replace every x in the function with 0, you get a y-intercept of 0. So all we've really determined so far is this graph goes through the origin. Now what about the symmetry? And again, I'm using kind of scrap pieces of paper here. The symmetry is found by finding f of negative x. Well, remember that f of x is x over x squared plus 1. F of negative x is found by replacing x in the original function with negative x and then simplifying. And if we simplify f of negative x here, we get negative x on the top and we get positive x squared plus 1 on the bottom, and that's equal to negative 1 multiplied by x over x squared plus 1, which is equal to negative 1 multiplied by f of x, and that means that the symmetry is odd. So we can add that to our list. There are no vertical asymptotes. The reason there are no vertical asymptotes is vertical asymptotes occur when the denominator of a rational function is equal to 0. So when I look at the denominator, it's not possible for x squared plus 1 to equal 0. The horizontal asymptote would be found by determining the limit as x approaches infinity of the function. And the rule that we learned the other day is you're going to divide every term by the highest degree term in the expression, which is going to give us the limit as x approaches infinity of 1 over x in the numerator over 1 plus 1 over x squared in the denominator. At large values of x, both 1 over x and 1 over x squared will approach 0. Which means that we're going to get 0 over 1 plus 0, which is 0 over 1, which is 0. That means that we have a horizontal asymptote at y equals 0. And that's the x-axis. It may be the case that some of you were a little bothered by the fact that the x-axis is going to be a horizontal asymptote, and yet there is an x-intercept. We'll talk about that when the time comes. We don't need to worry about it right now. All of this stuff that we just did, this summary that you're looking at here, is just the preliminaries. We want to get down to business here and talk about our first and second derivatives. But I don't want to spend time in this lesson differentiating the original function. I'm giving you the derivative here. And the derivative would be found by using the quotient rule, because the original function was x over x squared plus 1, but we're not going to worry about that in this lesson. That is the derivative right there, and that means that we have only two critical points for the derivative. They are both the values of x that make the derivative equal to 0. There are no values of x that make the derivative undefined. My first derivative chart is going to go from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. And across the top, I can put all of my factors, 1 plus x, 1 minus x, and x squared plus 1 squared. I'm doing this, of course, so I can determine my derivative, and I'm finding the derivative so I can determine what my function is doing. So we fill in all of the positives and negatives. Just to go through this briefly, you're putting in a negative if the factor that's indicated in that column is negative in the interval. So from negative infinity to negative 1, I'm saying 1 plus x is negative, because if I put a number from that interval in there, I will get negative. As soon as I pass negative 1, that first factor becomes positive. So I'm just looking over my choices here, and they all look good. By the way, this third column is all positive because it's x squared plus 1, which will always be positive. When I multiply those three factors together, negative times positive is negative. Positive times positive times positive is positive. And then positive times positive is negative. What does that tell us? It tells us that the function is decreasing, then increasing, then decreasing. So we are going to have a minimum at negative 1 comma something, and we are going to have a maximum at positive 1 comma something. And I'm really not worried about what those coordinates are. If you wanted to determine the coordinates, you would put those numbers into the original function. All right, let's move on to the second derivative. Well, it turns out if you take the time to differentiate the first derivative, you will get this expression. And again, the reason why I didn't include finding the derivatives in this lesson is it would take us forever just to find the derivatives. My critical numbers for the second derivative would be 0 because of a factor of 2x in the numerator, and plus or minus the square root of 3 because of the x squared minus 3. That means that my derivative chart, which is a second derivative chart, will have an interval from negative infinity to negative root 3, from negative root 3 to 0, from 0 to positive root 3, from positive root 3 to infinity. And just a double check, and it's more for my sake than yours, but it's a good idea for you to check as well when you're doing your own work. If you have a domain from negative infinity to infinity, the number of intervals you will have in your chart is one more than the number of critical numbers. So if I have 3 critical numbers, I should have 4 intervals, and I do. Across the top, I'm going to put all of my factors, 2x, x plus root 3, x minus root 3, and then x squared plus 1 cubed. And again, I'm doing this so I can determine the derivative, which happens to be a second derivative, and I'm doing that so I can determine something about the graph of the function. So I'll fill in the numbers. 2x is negative in these two intervals. As soon as we pass 0, it becomes positive. X plus root 3 is negative, and then when we pass the 0 of that factor, which is negative root 3, it becomes positive. x minus root 3 will be negative until we pass the 0 of x minus root 3, which is root 3. Then the factor becomes positive. X squared plus 1 cubed is positive everywhere because x squared plus 1 will be positive. So we multiply these things together and we get a negative for the second derivative in the first interval. We get a positive for the second derivative in the second interval. In the next interval, we get a negative second derivative, and in the final, we get a positive. What does this tell us about the graph? Since the second derivative is negative in the first interval, the function is concave down in that interval. In the second interval, the second derivative is positive, which means it's concave up in that interval. Then the second derivative is negative, it's concave down. Then it's positive, it's concave up. So we have concavity changing and going from a negative concavity to a positive concavity. That means there's an inflection point at negative root 3. In fact, we're going to have a total of 3 inflection points. We are going to have an inflection point at negative root 3, comma something. We will have an inflection point at 0, comma something, and at positive root 3, comma something. I don't care about the y coordinates. This is all about locations in terms of x. If you wanted to know the y coordinates, feel free to find them. And you may have to do that as part of your assignment. So now I would like to take a look at the graph with you, because I've got the graph set up already so that we can look at it. So what did we say about the graph? What did we learn about the graph? We learned that there was only one x-intercept and it was at 0, and that was also a y-intercept. We said that at x equals 1, there was a maximum. We said that at x equals negative 1, there was a minimum. We said there was an inflection point at x equals 0. Now I'm going to exaggerate this, but if you look to the right of 0, it is concave down. When you look to the left of it, it is concave up. That's an exaggeration, but the concavity is concave down to the right of 0 and concave up to the left. We said that at the square root of 3, let me evaluate in decimal form the approximate value of the square root of 3. It's about 1.73. So if I were to look at root 3, which is about here, I can see that there is an inflection point. Again, I'm going to exaggerate things here, but when I look to the left of that point, I can see that it is concave down. And when I look to the right, I can see that it is concave up. Similarly, there is an inflection point at negative root 3. I can see that on one side of that inflection point, it is curving in a concave down fashion. On the other side, it is curving in a concave up fashion. Again, overly exaggerated. I can also see that this graph is asymptotic to the x-axis. If you were to extend these curves on the left and the right to positive and negative infinity, you would discover that they get closer and closer and closer. And finally, you can see by looking at the function that it is odd. I don't mean what a peculiar looking function, I mean it has odd symmetry. So that's example 1. So if we take a look at example 2, which is f of x equals x raised to the third, x plus 3 raised to the 2/3. I'm going to save us a bit of time here. There are no asymptotes. Asymptotes only exist with a rational function. In other words, there must be a denominator, and there isn't one. There is no symmetry. If you put negative x in for x in the original function, you will be left with kind of a hodgepodge of positives and negatives compared to the original function. When we look at the x-intercepts, the x-intercepts are the values of x that make the factors equal to 0. Well, we have the cube root of x, which means that when x is 0, the cube root of x would be 0. And then we also have x plus 3, which means that we have a second x-intercept of negative 3. Y-intercept is found by replacing x with 0 in the original function. So we are going to have a y-intercept equal to 0. No asymptotes, no symmetry, really big deal. All we've discovered is the x-intercepts of the function and also the y-intercept. So now we can get started with our first derivative chart. And if you were to find the first derivative, that's what it would be, which means we're dealing with the following critical numbers: -1, 0, and -3. We have to put these in order when we develop the intervals for our subdomains. So I'm going to go from -infinity to -3, from -3 to -1, from -1 to 0, and from 0 to infinity. Again, everybody, if we have 3 critical values, we have 4 intervals. So what do we have here? We have for factors x plus 1, we also have x to the 2/3, and then we have x plus 3 to the 1/3. We are doing this so we can determine the first derivative in terms of positiveness or negativeness, and we're doing that so we can determine whether the function goes up or down. X plus 1 is negative until we pass -1, after which it becomes positive. X to the 2/3 is positive everywhere because saying x to the 2/3 means you're going to take the cube root of x and square it. And even if x is negative, when you take the cube root of negative, you will get a negative, but then when you square it, you will get a positive. X plus 3 is going to be negative in this interval, and that means x plus 3 to the 3rd will be negative, because a power of a 3rd means a cube root. So when x plus 3 is negative, the cube root of x plus 3 is negative. When x plus 3 is positive, the cube root of x plus 3 will be positive. What does this tell us? Well, we multiply our positives and negatives and get a positive for the first derivative in the first interval, a negative in the second interval, a positive in the third, and a positive in the fourth, which tells us the function is increasing, then the function is decreasing, then it is increasing, then it is increasing. What have we learned about the function? Well, if the function is increasing, then decreasing, there is a maximum where it changes from increasing to decreasing. So there is a maximum at -3 comma something, and I don't care about the y coordinates today. Then the function is decreasing all the way up to -1, and after -1, it's increasing. Well, that must mean there's a minimum at -1 comma, who cares? This other critical point at x equals 0 didn't yield a max or a min. There's nothing there. Well, there's something there. We'll get to what it is when we take a peek at the graph later. Now I need to do a second derivative chart. Well, it turns out in many ways, the second derivative is simpler than the first derivative, which is an odd thing. It's a peculiar thing. In this particular case, the second derivative has only two critical values of x, 0 and -3, which means our second derivative chart goes from -infinity to -3, from -3 to 0, and from 0 to infinity. And it would be a fatal mistake if we didn't include the -2 in our second derivative chart. We have -2 as a factor, we have x to the 5/3 as a factor, and we have x plus 3 to the 4/3. Why are we doing this? So we can identify whether the second derivative is positive or negative, so that we can identify the shape of the function. -2 is negative everywhere. Now, x raised to the 5/3, we want to be very careful with this one. 5/3 is an odd exponent. And what that means is if x is negative and you take a negative raised to the 5 and then take the cube root, you'll get a negative. If x is positive, when you raise it to the 5 and take the cube root, it will be positive. My point is merely that if x is negative, x to the 5/3 is negative. If x is positive, x to the 5/3 is positive. X plus 3 to the 4/3, on the other hand, is positive everywhere because it's raised to an even exponent. So whether x plus 3 is positive or negative has no bearing on the situation, because we're going to raise it to a 4 at some point, making it positive. When we take a look at the second derivative by multiplying the positives and negatives, the second derivative is positive, then it's positive, then it's negative, which means that the graph is concave up, and then concave down. By the way, most people don't need this, but some people do have difficulty associating a positive second derivative with concave up. Well, if you have ever met a positive person, generally speaking, this is what they look like. And if you take a look at the shape of their mouth, that is concave up. They're positive. Somebody who's negative walks around all day with that frown, that upside down smile, which is concave down. So we only have one inflection point. We have an inflection point where it changes concavity. It goes from concave up to concave down. So that is going to be at 0, whatever. Well, it turns out to be 0, 0 because that's an x-intercept. Let me show you what the graph of the function looks like now, and we're going to go through every single piece of information that I figured out with you. This is what the graph of the function looks like. Now, one of the things we determined was that it was concave up from -3 to 0. And you can see that it's concave up from -3 to 0. We also saw that it was concave up from -infinity to -3. And in fact, -3 was a critical point of the second derivative, but it didn't turn out to be an inflection point. It was concave up before -3, and it continued to be concave up afterwards. So what we have here is a cusp. This sharp point right here is a cusp. We also saw that it was concave up to 0, and then after 0 it was concave down, which meant 0 was an inflection point. We saw, I believe, and I might have to go back and check, but I believe we saw that at -1 there was a minimum. I'd better just take a quick peek Yes, we had a minimum at -1. So we take a look at the graph. Is there a minimum at -1? Yes, there is, right here. And again, I don't care about the y-coordinate. You're certainly welcome to find the y-coordinate, but at -1, there is a minimum. We also saw that at -3, there was a maximum. Well, there's a maximum. Everything matches. There's no asymptotes. This is the thing I love about this kind of math. Everything we learn in theory is actually true when it comes to looking at the graphs. There's no exceptions to the rules. So that's pretty much it for the lesson. I feel as though I went along here at a pretty good clip at times, but again, same as always, if you feel that I was going a little bit fast, you can slow down by pausing the video, right? It's not something that you have to furiously try to write stuff down. You can watch the video multiple times if you like. Remember that my goal in this course is not for you to do a whole bunch of math. My goal in this course is for you to get better at math, and you have to take the initiative and decide what you're going to do to get better. It's the same as if we were sitting in a desk at good old WCHS. You're just at home now, and you have to decide how much you want to do. On page 229, number 2, there's C, D, E, F, and K. I don't think it says to graph anything. You certainly don't need to graph anything. But I think after you're done collecting your information, it's not a bad idea to graph things on your calculator and see if they match up. Anyway, have a great rest of the day. Work on some of these problems. We've got a Google Meet tomorrow in period 4, so if you need help, please feel free to come by, and I'd be more than happy to help you out. Have a great rest of the day, you guys. We'll talk to you later.